Good evening, everyone.
Good evening, ma'am. Good evening, ma'am.
Yeah. So today we will quickly recall the previous week's topics, and the main topic we are going to see today is equivalent matrices and similar matrices. Okay, so these are the topics we are going to see today. So first, let us quickly recall the things we have seen in the previous session, and also a few more topics from week 6. Okay. So in the previous session, we saw what is mean by a monomorphic linear transformation or a epimorphic linear transformation and also isomorphic linear transformation. We saw some examples for this, and we saw what is mean by nullity and rank. We saw that kernel is a subspace of the vector space V, and the range space is a subspace of W. So this is from the domain and this is from the codomain. And nullity is nothing but the dimension of this null space, and rank is dimension of this range space, right? And we saw some equivalent conditions that T is a injective linear transformation if and only if the kernel is 0. So kernel is 0 means what? The nullity is 0, right? Dimension of the kernel is your null space. So nullity is 0 in this case. Okay. And a linear transformation T from V to W is surjective, that is on to if and only if your image of T, that is the range space of T, is equal to W. Okay. So in this case, what happens? What is the dimension of your range space of T? It is your rank. And so this rank of T is equal to dimension of V when T is surjective. Okay. And when a map is both injective and surjective together, then we call it an isomorphism. So if we can make a map T from V to W, if we can find a linear transformation which is isomorphic from V to W, then we call V and W to be isomorphic vector spaces. Okay. So V and W are isomorphic vector spaces if we can find a linear transformation which is isomorphic from V to W. Okay. So an important result we saw here is that you take any n-dimensional vector space, whether it is from matrix space or a subspace of the Euclidean space, if it has dimension n, then you know that it is isomorphic to Rn. Okay. So we saw several examples for this. Okay. And then we saw the matrix representation of a linear transformation. So if V and W are vector spaces and T is from linear transformation from V to W, you have two bases. One is for V, another is for W. Okay. In that case, how to express T as a matrix with respect to this basis beta for V and gamma for W. So the expression is given here. So this matrix, how did we find? We first find what is the transformation, the image of the basis vectors in V. So the TV1, TV2, TVN, this we find. And then we write these vectors as a linear combination of the basis elements of W. These coefficients, you have to arrange them in the columns for the matrix A. So this is with respect to beta and gamma. Okay. So this is your matrix corresponding to a linear transformation T with respect to basis beta and gamma. Okay, fine. So I just want to add one example here because this in the previous class what we saw was that T from some Rn to Rm. So both were Euclidean spaces. So this example was different. So I thought let us do it in class. So here your T is from the set of all 2 by 2 matrices, real matrices, to the set of all 2 by 2 real matrices given by this. T of A is equal to PA, where P is a fixed matrix. Okay. The entries of P are fixed. They are A, B, C, and D. Okay. So now if you are considering this basis for both domain and codomain, okay, you are considering this ordered basis. So what is the linear matrix corresponding to this linear transformation with respect to the basis beta for both domain and codomain? So can you tell what are the steps involved? What are the steps involved here?
A into 1 0 0 0.
See, let us say maybe we can give some name for this matrices V1, V2, V3, V4. Okay.
AV1 plus BV2 plus CV3 plus BV4.
Why? See, what is that the first step we do? We first find what is TV1, TV2, TVN,
Okay.
right? So that is the first step. So let us do the same here as well. So what is TV1? So that is T of this matrix 1, 0, 0. This is nothing but P times of this matrix. So A, B, C, D into 1, 0, 0, 0. So what is the matrix? A, 0, C, and 0. Is that fine? Okay. Same way, what is TV2? It is A, B, C, D into 0, 1, 0, 0. Okay. So this is now
This
0,
will be 0B, 0D.
or A. This is 0, this is A, right?
Yeah. 0A,
0 and
C.
C. Okay. Now what is TV3?
EV3 will be ABCD.
A, B, C, D into 0, 0,
0,
1, 0.
0.
So this is now
It will be B,
0,
B0.
D, 0. Okay.
And P of E4 will be the column interchange of TV3.
Mm. So here you see, you have, this is 0, 1. So you have 0 and then B, 0, D.
D.
All right. Okay. So now what is the next step? The next step is that we have to write these as a linear combination of the basis of the codomain. Here codomain also has the same basis. So how to write this TV1 as a linear combination of this basis elements? AV1 plus 0V2 plus CV3 plus 0V4. Is that fine? The first one, here it is A, so AV1, and then here it is 0, so 0V2, and then here it is C, so CV3, and then here it is 0, so 0V4. Fine? Okay. So now for this, can you tell how to write it as a linear combination of the basis vectors?
AV2 plus EV4.
Yeah, 0V1 plus AV2 plus 0V3 plus CV4. Okay. And then here BV1 plus 0V2 plus DV3 plus 0V4. And this one 0V1 plus BV2 plus 0V3 plus DV4. Fine. Up to this you all understood, right? Okay. So now how to write the matrix? So we have to write these coefficients in the column. Okay. So let us write. So what is the name of this matrix? Basis. It is beta. Okay. So T with respect to beta is given as A0, C0. Okay, A0, C0. All the coefficients of V1, V2, V3, V4. And here 0, A, 0, and C. 0A, 0C. And then B, 0, D, 0. Can you tell what is the last column?
0B, 0D.
Yeah. Okay, so this is the linear matrix corresponding to this linear transformation. Okay, so here you see the corresponding matrix is of size 4 by 4. Okay, so the procedure is exactly the same, where even though your vector space is different compared to this, the procedure is exactly the same. Okay, so in the exam, even if you have a matrix example, I guess you know how to do it. Okay, fine. Okay, so the next topic today we are going to see today is finding basis for null space and range space by row reduced echelon form. Okay, so given a linear transformation, okay, how to find a basis for the null space and the range space of this transformation T. Okay, for this we are going to use row reduced echelon form. So what are the steps involved? The first step is that, so first we have to find what is the matrix A corresponding to the basis for the codomain and a basis for the codomain. Okay, so usually we are considering the standard ordered basis. Okay, in the case of matrices, for example, for the 2 by 2 matrices, this is the standard ordered basis. Okay, so if it is the matrix case, don't wonder what it is. It is this. This is called the standard ordered basis for the 2 by 2 matrices. Same way you can generate for 3 by 3, 4 by 4 any matrices. Okay, fine. So after you find the matrix, you do row reduction. Okay, and find the reduced row echelon form for this matrix A. Okay, and call it R. Now you find what are the solutions of Rx is equal to 0. That gives you the basis of null space. Okay, and what are the columns corresponding to the pivot elements? Okay, those columns will give you the basis for the range space. Okay, so the vectors C1, C11, C22, all these vectors, they are forming a basis of null space. Okay, so what are these? So this is V1 dash, this is V2 dash, this is Vk dash. Okay, so these are the solutions of your Rx is equal to 0, and this forms a basis when you know that it is belonging to the kernel of T. Okay, and no. Here, I guess I wrote something wrong. So okay, take any set of vectors. So it forms a basis of a null space of A precisely when this particular vectors belongs to kernel of T, where these are linear combinations given by this. So let us maybe do a problem and then we come back here and see what is going on. So that case, in that case, you can understand what is going on here better. Okay, so let us first do a problem to understand the steps clearly. So consider this problem T from R4 to R3. Okay, so you are given Tx1, Tx2, Tx3, Tx4 is this. So you know what is the standard basis for both R4 and R3. So let us call the standard basis for R4 as beta. So what it is, what are the basis vectors? These are the standard basis vectors for R4. Now same way, what are the standard basis vectors for R3? Okay. So now with respect to this, if you want to find a matrix, what is the first step? Can you tell? Maybe we call this V1, V2, V3, V4. This is, let's say, W1, W2, W3. What is the first step to find the matrix? Yeah, what is the first step?
TV1.
Yeah. TV1 is equal to the answer is 2, 1, 1. And what is TV2? What is TV2?
4 3
4
1
3
4 3
4
1
3 1, yeah. And TV3
6 0 6
6 0
0 6
6. And what is TV4? 8 5 and 3. So what is the matrix with respect to this given beta and gamma? Here it is standard basis, so we don't worry about what is the linear combination. It is going to be just these coefficients only, right? So straight away we can write the matrix. So what are the matrix elements?
2 1 1,
Yeah, 2
4 3 1,
2 1 1, 4
4
3
3
1,
1,
6 0
6
6
0 6, and then
8
8
5
5
3.
8 5 3. 8 5 and 3. So this is your step 1, right? So this is your step 1. So finding the matrix corresponding to the linear transformation. Okay. Now the step 2 is we have to find the reduced row echelon form. Okay. So for finding the reduced row echelon form, okay, so you can do any kind of row operation. Maybe I start with R3 going to R3 minus R2. So what is that matrix you will get? 2 4 6 8 1 3 0 5. What about the last row? R3 going to R3 minus R2. So 0 minus 2 6 and then again minus 2. Is that correct? Okay. And for the next transformation, I can do R2 going to 2R2 minus R1. So what will you get? 2 4 it is 6 minus 4, so it is minus, it is 2. I guess it is better if I take R1 minus 2 R2. Both the column will be the same in that case, I guess. So maybe I'll write R1 minus 2 R2. So in that case, you will get 0. 4 minus 6 is minus 2. And then 6 minus 0. And then 8 minus 10. So minus 2. Sorry, here it is 6. Okay, so 0 minus 2, 6 minus 2. So can you tell what should be the next elementary row operation? R3 going to
minus R2
R3 minus R2. Okay, so you get 2 4 6 8 0 minus 2 6 minus 2 0 0 0 0. Okay, and then you can take R2 going to R2 divided by minus 2. So you get 2 4 6 8. Also you can divide R1 simultaneously here. So we are not using other rows. So maybe at the same step I can do R1 by 2 and R2 by minus 2. So 1 2 3 4 0 1 minus 3 1 0 0 0 0. Okay. So now is this in reduced echelon form or echelon form or reduced echelon form?
Echelon form.
Right? So we need to do one more step to make this reduced echelon form. Okay, so let us now do R1 going to R1 minus 2R2. Okay, so what will be the answer? 1. Here it will be 0, and then here it is going to be 9, and here 4 minus 2, 2. Is that fine? Okay. So we have found the reduced echelon form. Okay, so this is your matrix R. So now let us call this as your matrix R. Okay, so now the next thing you have to do is that, so what is your step 3? So you have to find what are the solutions of this matrix Rx is equal to 0. So, sorry. So you write Rx is equal to 0, 1, 0, 9, 2, 0, 1, minus 3, 1, 0, 0, 0, 0, x1, x2, x3 equal to 0, 0, 0. Okay. Up to this, is this fine? Yes. Okay. So the next step is that x1 plus 9x2 plus 2x3 is equal to 0. And this is x, sorry, here I missed one more vector here. It is x, up to x4, right? x1, x2, x3, x4. Here one more 0 is there. So x1 plus 9, x3 plus 2, x4 equal to 0. And here it is x2 minus 3, x3 plus x4 is equal to 0. Okay. So here if we can put some values for x3 and x4, then you can find a solution for this space. So for example, if I am taking x3 is equal to 1 and x4 is equal to 0, then what about x1 and x2? Can you tell what is x1 in this case? What is x1 in this case?
Minus 9?
minus
Minus 9. And what is x2?
3.
3. Okay. So the vector we have got here is minus 9, 3, 1, 0. Okay. And what about maybe let us consider x3 is equal to 0 and x4 is equal to 1. In this case, what will be the answer for x1?
Minus 2.
It is minus 2 and x2 is, and x2 is
Minus 1.
minus 1. Okay. x2 is minus 1. So the vector here correspondingly is minus 2, minus 1, 0, 1. Okay. So now these form a basis for the solution space of Rx is equal to 0. Okay. So you know that there are two elements in the null space because here you have two independent variables x3 and x4, right? So here you see that what is the null space
2.
of A here? Sorry, basis of null space of A here, or A or T, either way you can write. Yeah, what is that? Minus 9, 3, 1, 0, minus 2, minus 1, 0, 1. Is that fine for everyone? Yes?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So now we have found what is the basis of your null space of T. Next, what is your basis for range space? How do you find? For basis of range space, you look at what are the pivot elements. Can you tell what are the pivot elements? So you have one pivot element here and another pivot element. So in which column do you have the pivot element?
First and
First and the second.
First and second. So you take the first and second column as your basis for the range space. Okay, so the first column is 2, 1, 1 and the second is 4, 3, 1. 2, 1, 1, 4, 3, 1. So these are the basis vectors of range T. You know that range is in R3 and null space is in R4. So that is why here you got elements from R4 and here you have got elements from R3. So did we answer the question given here? Find a basis for the null space and range space of T. So what are the steps involved? Let me repeat the steps. Please listen carefully. So first step is that you first find what is the matrix corresponding to the standard basis for both domain and codomain. So we have found what is the matrix first of all. And the second step, for this matrix, you find what is the reduced echelon form and you call it R. And in the third step, you find the solutions of Rx is equal to 0. Okay. And from the solutions, this set of solutions, they form a basis. From this solution, you can find a basis for the null space of T. Okay. And also, you can find a basis of range of T. From this row echelon form, you find the pivot elements. So the columns containing the pivot elements in your original matrix, that gives you the basis for the range of T. Okay. So the steps for finding null space and range space for a linear transformation. Is that clear for everyone?
Yes, ma'am.
Okay.
Ma'am, can you repeat the last line, please?
Yeah. So here to find the basis of range of T, what is that we have to do is that you look at the reduced row echelon form. You find what are the pivot column, pivot elements. So this is a pivot element and this is a pivot element. So what are the columns containing the pivot elements? You just see. It is the first and second column in this case. So the first and second column you take from the original matrix and that gives you the basis for the range of T. Okay?
Okay.
Okay. So what is the rank of this matrix? Can you tell? What is the rank?
2.
And what's the nullity?
1.
1.
Nullity is 1.
No, rank plus nullity should be dimension 2.
So nullity is 2 here, right? So how many elements you have in null space?
2.
Yeah, so the nullity is 2. All right? Okay?
Okay, ma'am.
Fine. So maybe I'll write here rank. See how many elements are in the basis. So rank of T is 2. And here you note that nullity of T is also 2. You have 2 basis elements in the null space. So nullity is actually the dimension of the null space. So the dimension is nothing but the number of elements in your basis. So both rank and nullity are 2 in this case.
Ma'am,
Yes?
here T is the represent of linear transformation.
Yes, here T is this linear transformation given to you.
Okay.
Ma'am,
Thank you.
is it true that nullity represents independent variables while rank represents dependent variables?
Sorry, what?
Nullity represents independent variables and rank represents dependent variables.
Yes, from this echelon form, if you see what are the independent variables,
Yeah.
see you see this and this, they are the independent variables and these two are dependent variables.
Okay.
So these two are representing your rank and the other two, it is representing the nullity. Yes.
Okay. Thank you.
Ma'am,
Okay. Yes.
when we see the independent variable and dependent variable, sorry ma'am,
Yeah.
we look at the column or range. Sorry, column or row.
We look at the columns because here we are looking at the pivot elements. So the columns containing the pivot elements we are seeing. So we are looking at the columns only.
Okay, ma'am.
Yeah. Okay. So I guess finding the basis of null space and range space for a linear transformation is clear for everyone. So next is rank nullity theorem. So rank nullity theorem is exactly the same like in the case of matrices. So first, maybe we'll recall what is the case of in the matrix case. If you have a m by n matrix, right? if you have an m by n matrix, then rank of A plus nullity of A is equal to n. This you know, right? Now, so if you have an m by n matrix, what will be the corresponding domain and range for a transformation corresponding to this matrix? Can you tell? What is the domain and range for a linear transformation corresponding to this matrix? What is the domain? No one knows, right? So Rn here is your domain and Rm is your codomain, right? So here what are you saying? Rank of A plus nullity of A is equal to n, and n is the dimension of your domain actually. Dimension of Rn, right? It is your domain. Okay. So the same we are doing in the case of transformation as well. So let T from V to W be a linear transformation. Then rank of T plus nullity of T is equal to dimension of your domain. Okay. So instead of T, you are having a matrix here, and instead of the dimension of domain, you are directly writing what is the dimension of the domain. That's all. Okay. So rank nullity theorem, whatever you have done in the case of matrix, it is exactly same in the case of transformation as well. Just that here the domain and codomain are mentioned as V and W. Okay. Fine. So let T from V to W be a linear transformation. If T is injective, you know that rank of T is equal to dimension of V. Can you say why? So what happens if T is 1 to 1? If T is 1 to 1, what do you know?
Nullity is 0.
Yeah. That is actually all are equivalent. Nullity is 0. So if nullity is 0 in the rank nullity theorem, then what happens? What do you get?
Full rank.
Right? So rank is nothing but dimension of V. Okay. So this is the case when T is 1 to 1. Okay. So next, if T is on 2. Here they are directly going to an isomorphism. Okay, fine. So if it is an isomorphism, T is 1 to 1 and on 2. Okay. So what happens? Your kernel of T is 0. So nullity is 0. Okay. And on 2 means what? What happens when T is on 2?
Rank
Yeah?
is equal to dimension.
Dimension of your
W.
codomain. Okay. So then what happens in your rank nullity theorem? Your rank you can rewrite with W and nullity is 0, and you have here dimension of V. So what is that you are getting? Dimension of W is equal to dimension of V. Okay. So if T is an isomorphism, you know that dimension of W is equal to dimension of V. Okay. So the domain and codomain will have the same dimension.
So, ma'am, does it mean that isomorphism always happens for like same Rn, like Rn to Rn?
Yes, either from Rn to if it is the domain and codomain on Rn, yes. Otherwise, if you have subspaces, different subspaces, let us say W1 and W2 are different subspaces. Maybe it is from some Rn and this is from some Rm. But still, if you have dimension W1 is equal to dimension W2, then it is possible that you can find isomorphism from W1 to W2.
Okay, okay. Thank
Okay.
you.
Just that the dimension should be the same. The spaces need not be the same. Okay.
Okay, okay.
It can be also a matrix subspace. It can be anything. Okay, just that the dimension should match. Okay.
Okay, ma'am. Yes, thank you.
Okay.
Ma'am,
So yeah,
can you give the one example of 1 to 1 and on to, please?
I guess we have done some examples. Maybe I give you a very simple example. Okay.
Ma'am, with
Yeah.
satisfy the range T equals to dimension of V.
Yeah. Yeah, what's the problem with that? Rank equal to dimension of V.
Yeah. Take one example.
Okay, if you see here, for example, if I'm writing, maybe I'll write R3 to maybe another space, maybe R2 I'll write. R2 to space W. Let us say this is your V, and W I am writing set of all x comma 0 comma z, or x comma 0 comma y, such that x and y are in R. Okay, this is your space W. Okay, so now what happens? So let us say maybe T of x comma y I am defining as x comma 0 comma y. Okay, so what is the matrix corresponding to the standard basis? Corresponding to the standard basis, if you get, you see it is 1 0 0
1.
0 1, sorry, 0 0 1. So what is the rank of this matrix?
2.
Rank is 2. And what is the dimension of your V here? It is from R2, right? So
Yes,
what is the
ma'am.
dimension of V?
2.
Yeah. Okay,
Yeah.
fine. Okay. So find the rank and nullity of the linear transformation and verify the rank nullity theorem. Okay. So for this linear transformation, so what is the rank and nullity they are asking? So T of x comma y is given by 0 comma x. Can you first of all say what is the matrix corresponding to this with respect to the standard basis? Let us say beta is your standard basis. So what is the matrix representation? Yes. What is T of 1 comma 0? Okay, I guess I have to write 0 1,
0.
and then for T of 0 1 is 0 0.
0 0.
So this is the matrix corresponding to this linear transformation. So what is the rank of T then?
1.
Rank of T is 1. And for nullity, without using rank nullity theorem, how will you find what is the nullity? You have to see what is your null space spanned by. So can you see what is your null space of T here? So T of x comma y is equal to 0 0. When does this happen? If 0 comma x is 0 0, right? It means your x is 0. It means what is your null space?
0 comma x.
0 comma, maybe I will say y or x, that does not matter actually. Okay, so the first coordinate is 0. Okay, so this is your null space. Okay, so if there is only one vector in the, maybe I will say span of 0 1. So if there is only one vector in the span of a space, then what can you say about the dimension of that space?
1, ma'am.
Right? So now what is your rank nullity theorem saying? Rank plus nullity. Here in this case it is 1 plus 1, which is equal to 2, and that is nothing but the dimension of R2. So we have verified rank nullity theorem. Okay?
Ma'am,
Yes.
how to find the nullity of T equals to 1 here?
So what is nullity? Nullity is the dimension of the null space. So in the null space, the span has only one vector. It means this is a basis vector. So the number of basis vector is the dimension, right? So
Okay,
you
okay,
have
yes,
only
ma'am.
one vector in the basis. So you have nullity 1.
Yeah, got it.
Yeah.
Ma'am,
Yes.
can't we decide it directly looking into the matrix? Like the matrix is 0 1 0 0
Yeah.
with
From the
the.
matrix, we have found what is the rank.
Yeah, but with that also we can find that the nullity is 1, right?
So you are using again your rank nullity theorem. I don't want to use rank nullity theorem to say nullity because I'm going to verify rank nullity theorem. So without using this, I want to say nullity is 1. So you are saying since rank is 1, it is a 2 by 2 matrix,
No,
nullity should
I'm
be
saying
1.
because there is a one independent variable. That's why.
Oh, in that case, yes, you can say it that way as well. Of course, yes.
Okay.
Fine. All right.
Ma'am,
Yes.
can you scroll down the screen?
Sorry.
Yeah.
Yeah. What's the doubt?
No doubt, ma'am. I want you to take screenshot.
Oh,
Done, ma'am.
all right. So consider a linear transformation T from V to W such that dimension of V is 5, dimension of W is 7, and you are given that T is 1 to 1. So how do you find rank and nullity? Any idea how to find rank and nullity?
If T is 1 to 1, then rank will be dimension of V.
So what happens? Here you know that T is 1 to 1. So since T is 1 to 1, what do you know about nullity then?
0.
So in that case, what happens to your rank nullity theorem? Rank of T is equal to dimension of V. Okay. So here it means your rank, you will have to find rank. So your rank is 5. See here, there is another number given to you. It is just to confuse you. Here we are not using it at all. So that number is given just to confuse you. Okay. So here your rank of T is 5. Okay. Is this clear for everyone? Okay.
Yes.
So the next one, consider a linear transformation T from V to W such that dimension of V is 5 and dimension of W is 3, and here nullity is given as 2. Okay. Show that T is onto. How do we show that T is onto? So when is T is onto, what is the equivalent condition for onto?
The rank should be equal to the dimension of W.
Rank of T should be equal to dimension of W. So if we can prove rank T equal to dimension W, then you know that T is onto, right?
So we can do directly 5 minus 2 is equal to 3.
Yeah. So here you know that nullity of T plus rank of T is dimension of V. So here you have rank of T is dimension of V is 3 and nullity is dimension of V is 5 and 5, and here minus 2 means you get 3.
3.
So which is nothing but the dimension of W. So rank of T equal to dimension of W. Therefore, T is onto. Is this fine?
Yes, ma'am.
Fine. So can we find a linear transformation T from R4 to R3 with kernel 0? Okay. So since the kernel is 0, what can you say about the nullity?
It's 0.
Nullity of T is 0. So if nullity of T is 0, what happens to rank of T?
Full rank 4.
Yeah. It is dimension of R4, so it is 4 actually. But
Ma'am?
what is the matrix corresponding to this T? What is the order? What is the size of the matrix?
3 by 4.
It is a 3 by 4 matrix. So what can be the maximum rank for the 3 by 4 matrix?
3.
3.
It is less than or equal to 3. But here you are getting rank to be 4. Is this possible?
No, ma'am.
Okay,
No.
this is not possible. This is not possible. Okay, since the maximum rank can be 3, this is not possible. So we cannot find a linear transformation from R4 to R3 with nullity 0. Okay,
Ma'am?
so then, yes.
Kernel 0 means the function is on to 1 to, sorry.
1 to 1.
Okay.
Okay,
So
in this
that
case, it is
means
not
if the
possible.
domain is if the domain is bigger than the codomain, the linear transformation can never be 1 to 1.
Yes, it cannot be 1 to 1. So bigger in the sense the dimension is bigger. Yes, in that case,
Yeah.
it cannot be 1 to 1.
Okay.
See, you can see it with just some simple sets, okay, and functions. Suppose you are having 4 elements here, and you are having only 3 elements here. Is it possible that each one in the codomain will have a unique pre-image?
No.
No, ma'am.
It is not possible, right? That's all is the concept here also. Okay.
Okay. Thank
So
you.
these
We
4
can
elements
do
here are
we
the
can
basis
do with
elements. That is how
subspaces,
you can
right?
imagine. Yes.
We can do with subspaces within these, right? Like the transformation. Like no, even then. No, sorry, sorry.
Okay.
And
So I
like the same rule applies for the subspaces, right?
see here. Don't worry about what is a space or what is a subspace. All here matters is the dimension of the domain and codomain.
Okay. Okay. Okay.
Fine.
So, ma'am, instead of solving all these things, we can directly conclude, like if we find that it is 1 to 1 and the space is like 4 to 3, like higher space to lower space, we can directly conclude that it's not possible, right?
Yes, we have just given the reason here. Yeah, if you
Mm-hmm.
can remember what is the reason or understand it clearly, then you can directly write it is not possible.
Okay. Hmm.
Ma'am, do we have same kind of idea about subjectivity?
For subjectivity, yes, we can say actually. For example,
Like R3 to R4 subjectivity is not possible.
okay, let's see
If the
what
codomain is
happens if
bigger.
we are taking sorry R4, and what happens if T is on 2. If T is on 2, what happens to your rank of T?
It is 4.
Rank of T is 4. Okay, but you know already this matrix rank is less than or equal to 3, right?
Yes.
So it is not possible, right?
Okay.
But hold on, rank of T will be 4, and you see that it is not possible because the rank is maximum rank possible is 3. So similarly, just like we have given a condition for zero nullity, we also have a concept for full rank. Full rank is not possible when the codomain is bigger.
Okay. Either one is bigger, then the rank can't be full, right?
Yes.
Okay. Okay. So, like for rank to be full, the dimensions need to be dimensions need to be equal.
See, what do you mean by full rank? So for a 3 by 4 matrix, 3 is full rank actually, right?
Okay. Okay. Because 3 is the column.
Yeah. So here, don't maybe use the term full rank or anything. Maybe you say maybe if T is on to means it is not possible when domain is bigger. Okay. Maybe I'll write on to means codomain cannot be bigger. Bigger means, I guess you understand, the dimension is greater. Okay.
Okay.
And 1 to 1 domain cannot be bigger. That's all you need to remember or understand. Yes, this notation created problems. I will not use it. Okay, so this is what you need to remember. Okay, fine. So, okay, one more question regarding the same topic. Any injective linear transformation between any two vector spaces which have the same dimension must be an isomorphism. So it means what? You have T from V to W, okay, and you are given that T is 1 to 1. So this implies what is given is that this, and also it is given that dimension V is equal to dimension W is given to you. So they are saying that this will imply T is an isomorphism, they are saying.
Correct.
Yes.
So why is that correct?
Because nullity will be 0, so rank must be full.
Yeah. So you know that rank of T is equal to dimension of V. So that's why you get T is onto. So from this case, what you can say is that from rank nullity theorem, rank T is equal to dimension of V. So you know that this is dimension of W, and hence you know that T is onto. So T is both 1-to-1 and onto, and so T is an isomorphism. So the first option is fine. What about the second one? So the same setting you have T from V to W. You are given T is onto, and again dimension of V is equal to dimension of W.
Not
So
necessary, right?
again a similar reason only you will have, right?
Yes, it will be true as well.
Yeah, here because you know that rank of T is equal to dimension of W, and it is equal to dimension of V. It should be saying that this implies actually nullity is 0. Nullity 0 means T is 1-to-1. So 1-to-1 and onto together gives isomorphism. Is this clear for everyone?
Okay, yeah.
Yeah.
But ma'am,
Yeah.
we cannot say that the same dimension for domain and codomain must be isomorphic, right?
Actually, it is an if and only if condition. If domain and codomain are of finite dimensions and they are equal, then we can actually find a isomorphism.
So like they will always be isomorphic or
No, no, no,
maybe?
no. Of course, it cannot be always isomorphic, right? Because you know there are several examples for 2 by 2 matrices and 3 by 3 matrices, or any square matrix for which the determinant is 0. It means it is not an isomorphism, right? But we are saying there exists. It means you can find. That's all.
If the determinant is 0, so what does that imply?
If determinant is 0, it means it is not invertible. That is, it can the corresponding transformation is not an isomorphism.
Okay.
Okay.
I don't understand properly, to be honest.
So what you said is that always any suppose your question was that
No, I
so
have confusion. It like if determinant is 0, so it can't be isomorphic.
it cannot be isomorphic.
Yes, but why?
Okay, so I guess I did not use that connection here. But
Yes,
the connection is that see if T is 1-to-1 and onto, okay, then only T is invertible.
okay.
Okay, so this is the connection. So when in terms of matrices, if you see, when do you say a matrix, so square matrix, n by n matrix, when do you say it is invertible? So you say it is invertible if
When the
rank
determinant.
of A is equal to n, or you say nullity is 0, right?
Okay.
It is
Yes.
nothing but this condition, 1-to-1 and onto.
But like or, you're saying or, so isn't it like 1-to-1 or onto?
No, 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 no. See, if it is 1-to-1, obviously it will be onto.
Oh,
That
yes,
is
yes,
what
yes.
we saw here
Oh,
also.
yes, yes, yes. Okay, okay.
Mm.
So if it is invertible, it will be isomorphic, otherwise it won't be.
Yes, the
Okay.
corresponding matrix will be if it is invertible, then the transformation is isomorphic. Yes.
But like, what is the logic behind it?
What is the logic? That is what I said. If it is invertible, you know the matrix, corresponding matrix is having full rank and nullity is 0. It means it is 1-to-1 and onto.
Okay, that is okay. Okay, thank you, ma'am.
Mm. Okay. So the third option says that there does not exist any surjective linear transformation from R2 to R3. I guess this is what we saw here. If the codomain is bigger, then it cannot be onto. So is this statement correct?
Yes,
There
ma'am.
does not exist any surjective linear transformation from R2 to R3. Is that correct?
Yes.
Yeah.
Correct.
There does not exist any injective linear transformation from R2 to R3. What do you think?
Wrong.
Not true, maybe.
So T from R2 to R3, T of x comma y is equal to x comma y comma 0. Is this injective or not?
Yes, it can be. Yeah.
It is
Yes, ma'am, it's
injective, right?
injective.
Yes.
Yeah.
So you see that this option is not correct. Okay. Fine. Okay, I guess we are almost at the end of week 6. Yeah, week 6 is over, so week 7 starts here. Okay, so now let us start with week 7. So the week 7 topic, maybe before introducing, I will ask just one question. Maybe this answer for this question we will cover in week 7. Maybe straight away you will not be able to see when we start week 7, but eventually you will get the answer for this question from week 6. So you saw that if T is any linear transformation from V to W, if you are taking different bases, okay, so let us say you are having some basis, maybe B1, B2 for V, and you are having some other bases C1, C2 for W. These are bases. Okay. And suppose you are having a matrix A, which is the matrix A is T with respect to B1, C1, and matrix B is T with respect to B2, C2. So now you know that these matrices are going to be different. Okay, it can also be possible that these if the domain and codomain are same, then you may also consider the same basis also. That is a different case. I'm just giving an example. Okay, what we saw is that different matrices corresponding to different bases of the same linear transformation are different. But don't you think there should be some relationship between these matrices?
Yes, ma'am, there should be.
Yes. What is that relationship? That is what we will be seeing soon. What kind of relationship it will be having? We will get an answer from the week 7 topic. Okay. Okay. So just remember this question. We will answer it soon.
So are they going to be dependent?
No, it's going to be something completely new. So let us see what is that concept.
Okay, okay.
Okay. So first we will see what are equivalent
Excuse me,
matrices.
ma'am. Before you start week 7, I just want to know. I want to let you know that I haven't gone through. I think many of us haven't gone through week 7.
Don't
Yes,
worry.
ma'am. We've also not gone to week 7 content.
Yeah.
Don't
So yeah.
don't worry. I will go very slowly, very step by step. I will tell everything. Okay. Because of the quiz, we have one session short. So I'm starting week 7 today itself. Don't worry. I will go step by step. Okay. I will not skip any step. Is that fine?
Okay,
Yeah.
yes,
Thank
ma'am.
you.
Yeah.
Yeah.
Ma'am, one request.
Yeah.
The last class document has not been uploaded. Please look into it.
Oh, I did not.
Ask,
I sent it right after the class. I sent it. Maybe I will send a
because we
reminder.
have got very less time for quiz too. So,
Yeah. I will right after this class. I will send a reminder to upload it. I don't know why. Just immediately after the class itself, I sent the
thank
document.
you, ma'am. Thank you.
Okay, fine. I'll take care. Okay. Yeah. Equivalence of matrices. What is mean by equivalence of matrices? Okay. Let us say you are having two matrices. Main condition is that both should be of the same order. Okay. We cannot talk about equivalence of matrices when they are of different order. Okay. The first point when we talk about equivalence of matrices is that both should be of the same order. Okay. So we consider two matrices, both of order m by n. Okay. When can we say these two matrices as equivalent is that if there is an invertible matrix P and an invertible matrix Q, okay, P is of order n by n and Q is of order m by m, such that B is equal to QAP. First of all, to see this, let us see whether the matrix multiplication is fine. For Q, the size is m by m. For A is an m by n matrix and P is a n by n matrix. So the resulting matrix should be of size. Yes, what is the resulting matrix
MN.
size?
MN.
M by n. Okay, so this is fine, right? So we say that A and B are equivalent if you can find two invertible matrices Q and P such that B is equal to QAP. Okay, so why the name equivalent? I will tell you. So for that, you should know what is an equivalence relation. Okay, what is an equivalence relation? Equivalence relation, take any set A. A can be any set. Okay, so on any set, if you take a binary relation, when do we call it as an equivalence relation? You say it as an equivalence relation if it satisfies this following three conditions. What are those conditions? A is equivalent to A. For example, I will tell you the very familiar one which you already know. Maybe I will use less than or equal to. Okay, this symbol. Okay, this is an equivalence relation. This symmetric property I cannot say. Maybe I will just put equal to. Equal to is an equivalence relation in R. Okay, so take any number. So take any number A is equal to A. The first condition, it satisfies, right? Okay, I'm just giving an example for you to understand it. And what is mean by symmetric? So if A is equal to B, you can also write B is equal to A, right? Right? So that is the property of symmetric. If A is related to B, then you can say B is related to A. So this is called as a symmetric property. So reflexivity means A is related to itself. And what is symmetric? If A is related to B, the implied relation is that B is equivalent, B is related to A. And what is transitivity? If A is equal to B and B is equal to C, then A is equal to C. Okay, so you see equal to is an equivalence relation because it satisfies reflexive, symmetric and transitive conditions. So if A is equivalent to B and B is equivalent to C, sorry, B is related to C, then you see that all of C is also related to A. Okay, so this, if a relation satisfies all these conditions, reflexive, symmetric and transitive, then such a relation is called a equivalence relation. Okay, so equivalence of matrices, this is an equivalence relation is what we are going to see. That is why we see that get the name equivalence. Okay, so this is an equivalence relation. How to see that? What is the first condition to verify equivalence? What is an equivalence relation? That you all understood, right?
Yes.
Yes. So for example, if you take less than or equal to, which property it will not satisfy? You can write any number is less equal to this number. So first property, reflexivity, is fine. But what about the second one? Second one, will it satisfy? Second one, will it satisfy? Suppose you say 2 is less equal to, say, can you say 3 is less equal to 2?
No, it's
No.
not.
So this is not possible. And what about the transitivity?
In this case also cannot possible transitive.
Transitivity is possible, right? So for example,
this
if you
case.
have 1 less equal to 2 and 2 less equal to 3, then 1
Yeah,
less
then
equal
it
to
is
3, right?
Yes.
So this 2 is there, but symmetry is not there. So it is not an equivalence relation. All these three, if it is satisfied, then only we call it as an equivalence relation. Okay. So there are several equivalence relation for different sets. So equal to is a very familiar example. So in the case of matrices, the equivalence relation we have used here. Let us see how it is an equivalence relation. The first thing we have to say is that A is equivalent to itself, right? First is the reflexivity property. So we have to say A is equivalent to A. It means what we have to find? We have to find matrices Q and P such that A is equal to Q, A, P. Obviously, what can be the options for Q and P? If you take Q to be the identity matrix of size M by M and P to be the identity matrix of size N by N, then you will get that A is equal to QAP, right? Because multiplying identity matrix is not going to change your matrix, right?
Yeah.
Q is your M by M matrix and P is your N by N identity matrix. Okay, so what did you get? A is equivalent to A, right? The first property, reflexivity, is satisfied. What is the second property? You assume A is equivalent to B and you want to prove that B is equivalent to A, right? So if A is equivalent to B, what do you know? There are invertible matrices Q and P. Q and P are invertible, and you can write B as QAP. Okay, so you can write B is equal to QAP. Now, what happens when I pre-multiply both the sides with Q inverse and post-multiply with P inverse? So, Q inverse B, P inverse, Q inverse Q, A, P, P inverse. So, what is that you will get? Q. What is Q inverse Q?
Identity.
And what is P
I-
inverse? So, this is of
Identity
size
matrix.
M and this is of size N. So, what is the right hand side?
A.
A. So you see that you have written A as Q inverse B P inverse. Okay. So maybe you can write A is equal to Q dash B P dash, where Q dash is Q inverse, P dash is P inverse, and Q dash and P dash are invertible matrices. So this means what? A is equivalent to B is equivalent to A. This means what? B is equivalent to A. Okay. So what we have got, A equivalent to B implies B equivalent to A. Is this clear for everyone?
1 minute, ma'am. Ma'am, this thing which you write, QP is invertible and B is equal to QAP.
Yeah.
Ma'am, is this your assumption? Like we are taking this assumption like QP is invertible and B is equal to QAP, and after that we are
Yes.
doing all this.
Yes. So we are assuming that A is equivalent to B.
Okay, and this also QP is invertible and B is equal to QAP,
See,
right?
if A is equivalent to B, that is the definition, right? What is the definition? If A is
No.
equivalent to B, there exist invertible matrices P and Q such that B is equal to
Okay,
QAP.
okay.
That is the definition.
Okay.
Okay. So we just use the definition. That's all. Okay. So again, using the definition only, we are saying since we have got invertible matrices like this, that is why I'm again saying B is equivalent to A. Okay. From the definition. So what is that we have proved? We have proved symmetric property that A equivalent to B implies B equivalent to A. So what is the next condition? We have to prove transitivity. So A is equivalent to B and B is equivalent to C should imply A is equivalent to C. This is what we need to prove next. So since we are now, what is the two condition we are assuming here? A is equivalent to B and B is equivalent to C. Okay. So if A is equivalent to B, you know that there are two invertible matrices Q and P such that B is equal to QAP. Same way, you know that there are invertible matrices Q dash and P dash such that C is equal to Q dash B P dash. Okay. So now what is it you need to prove? You need to prove A is equivalent to C. Okay. So now what have we done? What are you going to do? You have to find matrices. Maybe I'll call, I don't know, maybe some Q tilde and P tilde such that you can write C as Q tilde A P tilde. So this is what you need to prove. This is your claim. Okay. So what is that you already have? C is equal to Q dash B P dash. And you already know B, you can write it in this way. So let us replace B with QAP here. Okay. So Q dash QAP P dash. Okay. Now I'm just interchanging the brackets here. So Q dash Q as one matrix and P dash as another matrix. Okay. So if two matrices are invertible, what about the product? Will that also be invertible?
Yes.
Why?
Uh, Determinant is not zero. I remember.
Yeah. So if A and B are invertible, okay, then AB is invertible. Why? Because what happens to determinant of AB?
Determinant of AB is equal to determinant of A into determinant of B.
Yes, and
And
you know
since
both
A
are
and B
non-zero.
zero, it will not be zero.
Yeah.
Okay, and that is why you know that the product of invertible matrix is again invertible. So you can now call this Q dash Q as Q tilde and this A here and P tilde. So your Q tilde is just Q dash Q. You know that this is invertible. Again, P tilde is P dash, and this is also invertible. Okay, so we have found invertible matrices Q tilde and P tilde such that C is equal to Q tilde A P tilde. So what is that we finally proved? We proved that A is equivalent to C. It means what is this property? We have proved transitivity.
Transitive.
So here we have proved reflexivity, here we have proved symmetric, and here we have proved transitive. Okay, so if all the conditions are satisfied, then you know that this is an equivalence relation. Okay, so this is an equivalence relation. In matrices itself there are several equivalence relations. So this is one such equivalence relation. So don't think that only when the name is given like this, equivalence matrices, then only you have equivalence relation. It's not like that. There are several equivalence relations. Okay, so this is just one such example for the matrices. Okay, fine. Okay, show that A is equal to 120172 and B is equal to 211027 are equivalent. So what is that we need to prove to show that two matrices are equivalent? What is that we need to prove?
We have to prove like it's a symmetric, transitive, and reflexive.
No. That is for equivalence relation.
Okay.
Just to prove that two matrices are equivalent. See, two matrices are equivalent if there exists invertible matrix P and Q such that B is equal to QAP. Okay.
Okay.
So it means what? We have to find matrices Q and P such that B is equal to QAP. Okay. Since it is a first example, we are given with what is the Q and P. Okay. So quickly see whether these are invertible matrices. First one is identity, so nothing to worry. The second one is also having determinant non-zero, so it is invertible. Okay. So now B is equal to QAP. Is that true or not? Can we quickly check? What is QAP? We have to see. So Q into A should be just A, right? Because this is identity matrix. So this is just A because Q is identity matrix. So this is simply AP. And I'm writing what is A. And I'm writing what is P. Let us multiply and see what is that we are getting. So first we are getting 2, 1, 2. And then we are getting 1, 0, 7. And this is nothing but your B. So did we get that B is equal to QAP? Yes. So we can say that A and B are equivalent. Okay. So the process of finding this Q and P, it is not very simple for any matrix. Okay. It can be very complicated. Finding this P and Q can be very complicated. Okay. That is why for the first example, they have given Q and P. Okay. So if it is given that A and B are equivalent, then finding P and Q can be very challenging in many cases. Okay. Fine. Suppose you know that A is equal to this and B is equal to this are equivalent matrices. They are saying that they are equivalent matrices. And now they are given as what is your Q. So they are asking us to find the possible choices for P. How can we find it? Any idea how to find the possible choices for P? Any idea? Yes? Okay, first of all, can you tell me what is the size of the matrix P? It should be a 3 by 3 matrix, right? And since we don't know what is this 3 by 3 matrix, let us just give random constants, arbitrary constants like this. Okay, and we see what are the possibilities for these constants. Okay, So what is the relationship between all these matrices now? B is equal to QAP. This is the relation we have. So let us write what is this relation. You have A, B, C, D, E. Oh, I started with P rather than B. So what is your B? 1, -1, 0, 1, 2, 1. And this is given to be equal to 0, 1, 1, 0, 1, -1, 0, 0, 1, 1, and A, B, C. I guess someone did not mute. Please mute yourself. There is an echo. Yeah, thank you. So first let us multiply these two matrices. Shall we quickly multiply these two matrices? What is that you are going to get? The first term 0, second term 1, third term 1. What about this? 1, -1, 0. Is that correct? The matrix multiplication. Okay. So now let us do this matrix multiplication. You have D plus G, E plus H, F plus I, right? And then you have A minus D, B minus E, C minus F. Is that correct?
Yes, ma'am.
Yeah? Okay. So now let us equate the LHS and RHS. So what do you get if you equate the LHS and RHS? This equations, how many solutions do you think you have? So one such solution, maybe you can write. Maybe you can put one particular number for D, one particular number for E, and one particular number for F, and write what are the answers. Okay. Maybe you can, the simplest case, maybe you can take if D is equal to 0, then what is G? G is 1 and A is 1. And if E is 0, what is H?
Minus
-1, and B is
B,
B will be
2.
and if F is 0,
I equals 0.
I is 0, and
C is 1.
C 1. Okay, so this is just one possibility. So depending on it, we can keep on changing D, E, and F, and we can find various answers. So how many solutions does this system have?
infinite.
Yes. So P has infinitely. Okay, actually maybe I write in a different way. We have infinitely many choices for P. So this is the answer. So what is the question? You are already given two matrices which are equivalent, and you are given what is the matrix Q. They are asking finding the number of possible choices for P. So in this case, you got infinitely many solution here. That is why infinitely many many choices. Suppose if you have got a unique solution, then you have written 1. Suppose no solution means 0. Okay, so since the matrices are equivalent, definitely you should get some P and Q. So for this particular case, you got infinitely many choices. Okay, is this clear? This example, right? Is this clear, right?
Yes, ma'am.
Okay, fine. Okay, So in some particular case, we can actually find what are this P and Q. There is a specific technique to find what is your P and what is your Q. Okay. So let us see what is that particular case. Okay. So let us consider a linear transformation T from V to W. Okay. So a linear transformation T from V to W, and you have basis beta 1 and beta 2 for V. Okay. Both are the basis for V. And what is the plural for basis? Basis. ES is a plural for basis. Okay, so if you see ES, it means plural. Okay, and gamma 1 is equal to W1, W2, Wm, and gamma 2 is equal to X1, X2, Xm. These two are ordered basis for W. Okay, so we are having beta 1 and beta 2 for V and gamma 1 and gamma 2 for W. Okay, now A is the matrix of T with respect to basis beta 1 of V and gamma 1 of W. So it means what? A is equal to T. Okay, here you have beta 1 and here you have gamma 1. Okay, so it means what? You first find what is TV1, what is TV2, up to what is TVN. Okay, you express them as a linear combination of all these W's. Maybe one, C2. Yeah, I guess you have to mute. Please mute yourself. Yeah. Okay, in this way you have whatever the Cij, so that is your matrix here. Okay, and what is your B? B is the matrix of T with respect to beta 2 for V and gamma 2 for W. Okay, so it means what? TU1, TU2, TUN. All this you are expressing as a linear combination of X1, X2, and Xm. Okay. So these are your V. So what is A? A is a matrix corresponding to beta 1 and gamma 1, and B is another matrix corresponding to the same transformation T. Okay, but with respect to different bases beta 2 and gamma 2. Okay, now what do you know about A and B? Then A and B are equivalent. Then A and B are equivalent. Okay, so did we answer the question which we saw just before starting week 7? Yes. What was the question we saw before week 7? If we have two different matrix representation for the same transformation, what is the relationship between those matrices? Okay, the relation is that these matrices are equivalent. Okay, so what is the answer? You all got it right? Okay, and it satisfies the equation. So you know that if A and B are equivalent, you can find invertible matrices P and Q such that B is equal to QAP. So now how to find this matrices P and Q? There is this specific way which is given to you here. Okay, so for finding P, okay, for finding P, you express the elements of ordered basis beta 2 in terms of the ordered basis beta 1. So here you take the elements of beta 2 and express in terms of elements of beta 1. Okay, so that coefficients will give you the matrix P. Okay, and for finding Q, express the elements of gamma 1 as the linear combination of the elements of gamma 2. That will give you the matrix Q. Okay, so I guess this will be very abstract for you. It is quite abstract, but let us do some example. You will understand. Maybe I can repeat the steps if you want. So what is that given? You are given two bases for the domain and two bases for the codomain. Okay, and you have a matrix representation with respect to beta 1 and gamma 1, and you have another matrix with respect to beta 2 and gamma 2, and you know that these two are equivalent. So you know that if two matrices are equivalent, you can find invertible matrices P and Q satisfying this condition B is equal to QAP. So how to find P and Q? So for P, you use this basis for the domain beta 1 and beta 2. You express beta 2, specifically the second basis, beta 2 as a linear combination of beta 1. The coefficients give you the matrix P. And the other way around for Q, you express gamma 1 in terms of the elements of gamma 2. That coefficients give you the matrix Q.
So
Okay.
in all, for this P will give us from the domain, and Q will give us from the
Yes.
codomain, right?
Yeah. P from domain.
Domain. And Q from codomain.
Yes. Okay. So they satisfy the relation. Now B is you have B. This is your Q A P. Okay. So this satisfies, these matrices satisfies the relation B is equal to QAP. Okay. So let us do an example so that it will be clear for you. Okay. So you are given T from R3 to R2 be the linear transformation defined by T x1, x2, x3 is equal to this. Let A be the matrix representation of this linear transformation T with respect to the ordered basis beta 1 and gamma 1. Okay, and for B is the matrix representation with respect to another basis beta 2 and gamma 2. So we are asked to find all the matrices A, B, P, and Q. Okay, so first let us find what is A and B. What is A? What is the procedure to find A? So maybe we call V1, V2, V3. Okay, and this one I call, this is U1. I don't want to change notations. I don't want to confuse you. This is V1, U1, W1, X1. Okay, I use the same notation here. V1, this is W1, W2, W3. This is U1, U2, X1, X2. Right? This is the same notations here, right? Oh, I switched this too, I guess. So this is actually W1, W2. It does not matter actually, but I don't want to confuse you. That is why I want to use the same notation so that you can compare with the procedure given to you. Okay, so we call this, we give names for these vectors like this. Now tell me how to find A. A is actually the standard basis, so that is the simplest matrix. So can you tell what is TV1?
1 comma minus 1.
1 comma minus 1. And TV2?
1 comma 0.
TV2 1 comma 0. Yeah, TV3?
0 comma 2.
Yeah. So what is your A then?
1 1 0. Oh, 1 minus 1 1 0 0 2. Yep.
Okay. And then for finding your matrix B, so you have to find what is TU1, TU2, TU3. What is TU1?
1 comma 3.
1 comma, is it minus 3?
Oh, yes, it is minus 3. Sorry.
Yeah. And TU2?
2 comma 1.
Yeah. And TU3?
1 comma minus 1.
Yeah. Okay. Now you have to express this in terms of x1 and x2. So minus 3 x1 plus 1 x2. Right? And
Yes.
1 x1 plus 2 x2. Is that fine? And minus 1 x1 plus 1 x2. You see the basis is now in a different order. It is the standard basis, but the order is different. That is why every time you see it is mentioned as ordered basis. When you change the order, you see the matrix is going to be different, right? Even though the basis is the same, if the order changes, the matrix will change also. So now can you tell what is your B?
minus
One?
3.
Minus 3.
Sorry. It's not 1 minus 3. It's minus 3, 1. You have to write the coefficients, right? Minus 3, 1.
1, 2,
1,
minus 1,
2,
1.
minus 1, 1. So this is your A and this is your B. Now can you tell what is your Q and P? For P, what is that you need to do? You have to express.
It in terms of domain of.
Q1
So
in
let us
terms of
see.
P1.
For P, yeah, you have to express beta 2 in terms of beta 1. Okay. So what is your beta 2 here? Beta 2 is this set. Okay, so let us do that. Your beta 2 U1 is 1, 0, minus 1. So in terms of standard basis, it is very easy actually. So 1 V1 plus 0 V2 minus 1 V3. And U2 again, it is easy. 1, 1, 1. So 1 V1 plus 1 V2 plus 1 V3. And U3 is 1, 0, 0. So 1 V1, 0 V2, 0 V3. So what is your P then? 1, 1, 1, 1, 0, 0. Okay. And now what is your?
So quick question here: can the transpose of P will also? So if instead of writing it along column wise, if you write it along row wise, would that
It
have
will
an
not
impact?
satisfy the condition B equal to QAP.
Okay.
Okay. Fine. Now you have
Now we have to do it for
W1 and W2 in terms of X1 and X2. W1 is 1, 0 in terms of X1, X2. So your X1, 0, X1 plus 1, X2. Is that correct? 0, X1 plus 1, X2. Right? And W2 is 1, X1 plus 0, X2. Right? W2 is 0, 1. That is 1, X1. 1, X1 plus 0, X2. Right? So what is your matrix Q? 0, 1, 1, 0. Okay. Now let us verify whether it is true. So let us find what is QAP. Okay. So 1, 1. Maybe at first I will write what is QA. Then we'll multiply with P. 1. Sorry. Q is 0, 1, 1, 0. And your A is 1, 1, 0 minus 1, 0, 2. So what is the matrix you get? Minus 1, 0, 2. And then you have 1, 1, 0. Okay. And then let us do QAP.
Ma'am, sorry to interrupt you. Ma'am,
Yeah.
can you please upload the PDF of previous session?
Yes,
Kindly
already
student.
someone mentioned. I will do it. Okay.
Okay, ma'am. Thank you.
Yeah, fine. Okay. So what is the matrix multiplication here? Oh, I wrote the wrong matrix. Your P is 1, 1, 1, 0, 1, 0, minus 1, 1, 1, minus 1, 1. So what is the matrix multiplication here? Minus 1, minus 2, minus 3. And then minus 1 plus 2 is 1, minus 1. And then you have 1, you have 2, and then you have 1. Is that fine? And this is your B. Right? So this process of finding this matrices A, B, P, and Q. Is this clear for everyone? Yes?
Yes, ma'am.
Okay.
Ma'am, can you just explain how did you find Q from
Okay.
W to X, that part?
Yeah. So what is your Q? How do you find Q? You have to write gamma 1 in terms of the elements of gamma 2, right? So gamma 2 is 0, 1, 1, 0. Okay. So
Yes, yes.
here 1, 0, okay, is 0 times of 0, 1 plus 1 times of 1, 0. So this vector and this vector are exactly the same. Okay.
Okay.
So I'm just putting 1 here and 0 for the other one. And the same I'm doing for the other one also. 0, 1 is the first vector for me. So I'm putting 1 here. For the other one, I put 0. That's all.
Okay. So basically we have to write W1 in terms of X1, X2.
Yeah.
Okay, okay.
Okay. So this is how we are finding all A, B, P, and Q. Okay. So next we will see some properties or characterizations of equivalent matrices. Okay. Two matrices A and B, instead of so in all the time, instead of finding P and Q, are there any other way to check whether given matrices are equivalent? That is what we are going to see here. Okay. So two matrices A and B are equivalent if A can be transformed into B by a combination of elementary row and column operations. Okay. So you can actually here use both combination of row and column operation. Okay. So if you can use several elementary and row column operation and get the other matrix B, then you can say that A and B are equivalent matrices. Okay. Also, if you find the rank of the two matrices, okay, if they have the same rank, then also the matrices are equivalent. Okay. Now using this characterization, you can use any of the characterization. Okay. Can you check whether these two matrices given here are equivalent or not? Which property, whatever property you want, you can use. So what is the rank of A? What is the rank of A? You see the first two columns are actually dependent because second column is just multiple of the first column. Okay, so only one independent column is here in the first two. What about the third one? The first one and third one, are they independent? Yes or no?
I think
Yeah, 2, 1
they are
minus
not.
3, 2, they are independent, right? So what can be the rank of A? You have two independent columns.
Yeah,
Oh.
so 2.
Okay. Now what about rank of B? Again, you see that these two are dependent. So only one independent is there. This are they independent?
Yes, ma'am.
So you have rank of A is equal to rank of B. And so can we say A and B are equivalent? Okay. So the other method, actually it is quite lengthy, so I don't want to do it here. Maybe I give it as a homework. So method 2 we have done here, or characterization 2 we have done here. Try with method 1.
So like method 1, does it state that if we, after some elementary row operation, if we get the same row or reduced row echelon form, they are equivalent?
It is not reduced row echelon form. Yeah, okay, fine. You can say that way also. Yes,
Yeah.
if you get this matrix, yes, then you can. Here, remember, you can also use column operations.
Okay, okay.
Okay. So see whether you are able to obtain B from A using row and column operations. Okay, that is a homework. I leave it for you. Okay. So check whether A and B are equivalent. For this one, do we have to check anything? When we talk about equivalent matrices, in the beginning, what was the very first condition I told you?
Same order.
Yes, they should be of same order. Here it is 3 by 3 and here it is 2 by 2. So they are not of the same order itself. So straight away we can say, since A and B or of different orders, they cannot be equivalent. Is that fine? Okay. Fine. So now you have check whether A and B are equivalent. You have now 3 by 3 matrices. Okay. So can you check what is the rank of A and rank of B? What is rank of A and rank of B? Okay, for what is the determinant? This is actually a triangular matrix. So what is the determinant of A? Is it non-zero?
Yes.
No.
Yeah.
Oh,
So
yes.
what is rank of A?
3.
Yeah. Now what about B? Again, is the determinant non-zero? 1 times of 3 minus 1 times of minus 10 plus 1 and then plus 2 times of minus 6. So you get 3 minus 9, so plus 9 minus 12. It is actually 0. Did I do it correctly? Yes. So here rank of A is 3, but rank of B is not equal to 3. Did I do it correctly?
Yes, ma'am.
Right? So rank of B is not equal to 3. So the matrices have different rank. So what can we say? What is the result? Whether A and B are equivalent? What is the answer?
No.
Right? So A and B are not equivalent. So finding rank, again, there are several different techniques. Since it is a triangular matrix, I saw it is easy to use the determinant property here. That is why I use the determinant property. If you want to use echelon form, of course, you can do that also. Okay, fine. Okay. So if A and B are equivalent matrices of order m by n, investigate whether the following are true. Okay. So the very first condition, already you are given that A and B are equivalent. Okay. So what is given to you? A and B are equivalent. It means what? There exist invertible
QLP.
Q and P such that B is equal to QAP.
Take the transpose.
Yes. Now you want to see whether the transpose are also equivalent. So let us take the transpose on both sides. Suppose if you have a product of two matrices and you take the transpose, what happens to the transpose of the product?
B transpose into
Okay, the order gets changed. So B transpose is equal to P transpose A transpose Q transpose. Okay, so B transpose is P transpose A transpose Q transpose. So can we say A transpose is equivalent to B transpose from this? Right? If A and B are, sorry, if Q and P are invertible, what can you say about Q transpose and P transpose? Are they also invertible?
Yes, ma'am.
Right? The determinant will not change, right? So they are also invertible. So we have found invertible matrices such that B transpose equal to P transpose A transpose Q transpose. So we got A transpose is equivalent to B transpose. So this is fine. What about A square and B square? Can we obtain it by squaring? Is it possible if we do squaring? The matrix multiplication itself is kind of not possible. When you take QAP and again QAP, how do we do that?
they won't match. P and Q won't match like unless they are both of same order.
Yeah, right. So it means there is a possibility that they are not equivalent. So if you want to show that something is not equivalent, what is the technique you have to do? What is the technique?
Find one example where it doesn't.
Yes, you have to give some counter examples. Okay, so let me give an example for you. So you verify for whether it is true or not. Let us take this matrix A and another matrix, maybe, what is the other matrix? I guess this is correct. Yeah, this is correct. Now, what is whether are A and B equivalent? First of all, what is rank of A and rank of B?
1.
Both are 1, right? So we know that A and B are equivalent. Now, what about A square? What is A square? Quickly, what is A square? 0. This is 0. This is also 0. And this is 0. So A square is actually the null matrix. What about B square?
Same.
So 0, 0.
You get B.
Yeah. So rank of A square, what is rank of A square?
0.
0. And rank of B square?
1.
1.
So can they be equivalent?
No.
No.
No. So you see A square and B square are not equivalent. Okay. What about the third condition? AB and BA. Let us use the same examples. What about AB? You know already A and B are equivalent. What is AB? 0, 0, 0, 0. AB is 0, 0, 0. What is BA? 0. This is again 0. This is 1. This is 0. Is that correct? Yeah?
Yes, ma'am. Yes, ma'am.
So rank of AB is again 0 and rank of BA is
1.
1. So
Not
AB
equivalent.
and BA are not equivalent. Okay. So you see that AB and BA are not equivalent. So only A transpose and B transpose are equivalent. Okay. Fine. So up to this, is this clear?
Yes,
Okay.
ma'am.
So just like equivalent matrices, I told you already there are several other equivalent relations in matrices. Okay. So the concept of similar matrices is much stronger than equivalence matrices. This is also a equivalence relation. Okay. So what are similar matrices? Let us see. Okay. These similar matrices have very strong applications. Okay. Since you are studying this course in a data science course, so there is a concept called diagonalization. Okay. What is mean by diagonalization? Certain types of matrices you can once you know what is similar matrix, it is better to say, yeah, let us say there are certain types of matrices A which are similar to a diagonal matrix. You know how easy diagonal matrices are, right? So if you are able to look at a huge system as a very simple diagonal matrix, then how easy it is to understand the concepts there, right? So certain matrices A, since they are similar to diagonal matrices, that concept is called diagonalization. That is very helpful in dealing with certain types of data given to you. Okay, so that is where this application comes. So first let us see what are similar matrices. Okay, two matrices A and B of order n by n are said to be similar if there exists an invertible matrix P such that B is equal to P inverse AP. Okay, so what did we have in the previous case? In the previous case, we had rectangular matrices, whereas for similar matrices, we deal only with square matrices, only for square matrices of same order. Okay, and here instead of any other Q matrix, here it is directly P inverse. Okay, so B is equal to P inverse AP. Okay, so B is equal to P inverse AP. So if we have this condition, then we call the two matrices A and B to be similar. Okay, so again, verifying similarity is a equivalence relation is very easy. I can just quickly give the outline. I guess I have already done it for equivalence of matrices, so it is easy here also. So A is equivalent to A. Again, you choose P to be the identity matrix, and you can easily see that B is equal to I inverse AI. Right? And A equivalent to B implies B equivalent to A. That also you know. A is equal to P inverse, B is equal to P inverse AP implies P, B, P inverse is equal to A. I'm just pre-multiplying with P and post-multiplying with P inverse. Then I will get P inverse is equal to A. So this means B is equivalent to A. Sorry, A is equivalent to, okay, I wrote it. I started it from, yeah, I wrote it correctly. B is equivalent to A. Now, A equivalent to B and B equivalent to C should imply A equivalent to C. How is that? Again, you know that B is equal to P inverse AP and your C is equal to maybe let us say some Q inverse BQ. Then you know that C is equal to Q inverse P inverse APQ and Q inverse P inverse you can write as PQ whole inverse. Okay. So you see that A is equivalent to C. Okay. So A and B are equivalent matrices. Sorry, similarity. This similarity matrices are this similar matrices. This similarity is a equivalence relation. Okay, that is what we have proved here. Similarity is a equivalence relation. This is what we have proved here. Okay, fine. If two matrices A and B are similar, then they are also equivalent. It is obvious, right? So if two matrices are similar, you take B is equal to P inverse AP. You simply call this P inverse as Q. Then you see that A and B are equivalent, right? So it means what? Similarity implies equivalence. Okay, so this is a stronger condition. If you have this, then you have this equivalence also. What about the converse? Before I answer, what is your guess? Will the converse also be true?
No.
No.
Okay, so the converse need not be true. For example, so let us take these two matrices. Are they equivalent? Are they equivalent? These two matrices given here, are they equivalent? What about their ranks?
Yes, ma'am.
Yes,
Okay.
ma'am, they're equivalent.
Equal.
Okay. So what are the rank? Rank
Two.
of A is equal to
Two.
rank of B is equal to both are 2. So A and B are equivalent. Okay. Okay. Are they similar? Are they similar? Okay. Suppose let us say it is similar. Okay. Suppose A is similar to B. It means what? It means what? Then there exists P. So this symbol is there exists P invertible such that, okay, this is there exists, this is such that. So this is like this and this is like this. Okay. So there exists such P invertible such that P is equal to P inverse AP. Okay. So now what is your A here? What is your A?
Identity.
It is actually the identity matrix, right? So identity matrix, actually you can commute with any matrix, or you can actually write a P inverse P itself, because A is the identity matrix, so multiplication is just the same, and P inverse P is again the identity matrix 1 0 0 1. But is this possible that B is equal to the identity matrix?
No.
No.
So this is a contradiction. So our assumption, what was our assumption? A is similar to B is wrong. Okay, so A and B are not similar. Okay, so here A and B are equivalent, but they are not similar. Okay, the argument, is it clear? I have used a contradictory argument. So I first assumed that they are similar, but then I arrived at a contradiction. It means my assumption was wrong. That is, A cannot be similar to B. Okay, is this argument fine?
Yes,
Why
ma'am.
they are not similar? Okay. Okay, now check whether these two matrices are similar or not. How to check that these two matrices are similar or not? First of all, are they equivalent? Okay, if it is similar, then you know that they are equivalent. First of all, are they equivalent?
No, ma'am.
Okay, what is the rank of A?
Full rank 2.
And rank of B?
Less than, not 2.
Okay, so they are rank itself is not same. It means A and B are not equivalent. So if two matrices are not equivalent, then it cannot be similar, right? Because all similar matrices must be equivalent. So this implies that A and B are not similar. Here, do you understand the argument? They are not equivalent, and hence it cannot be similar, because similar matrices are all equivalent. Okay?
So if they are equivalent, then we cannot say that it will be similar. But if they are not equivalent, then certainly it is not similar.
Exactly.
Okay.
Okay? Fine. So which of this statement or is true, or verify these statements? It is A power n, B power n. Okay. So the very first statement is A or B is invertible. Either A or B is invertible, then AB is similar to BA. How to do that? Either A or B is invertible, then AB is similar to BA. How to do that? How to do that? Any idea? Okay. So suppose A is invertible. Okay. So you want to say that how you have to find P such that BA is equal to P inverse AB P. Okay. Now you are given that A is invertible. Now, if I take P to be A, then what will happen? Let us see. What is A inverse A? What is A inverse A?
Identity.
Yeah. So you have I times of BA. which is PA. Okay, so if you choose P is equal to A, then you have that BA equal to P inverse AB into P. So you see that AB is similar to B. Same way you can try for B. Okay, so I have assumed the condition A is invertible. Homework, do it with B is invertible. If B is invertible, prove the same. Okay, prove if B is invertible, how AB is similar to BA. See how you can use it. Okay, so this is first part. Second part, if A and B are similar, then A power n is similar to B power n. How to do that? So first of all, A and B are given to be similar. So it means what? There exists a P such that your B is equal to P inverse AP. Now let us say what is B square? P inverse AP into P inverse AP. Now what is P into P inverse? What is P into P inverse? Identity, right? So it means this is actually P inverse identity matrix multiplied with any matrix is itself. So this is A into A is A squared. So you see B squared is P inverse A squared P. So if you keep on repeating, you get B power n is equal to P inverse A power n P for any fixed n. Okay, fine. What about the third one? Up to this, is it clear?
Yes, ma'am.
Okay. What about the third one? If A and B are similar, then A transpose is similar to B transpose. So I guess we have done it in the case of equivalence matrices, the same technique. So you have B is equal to P inverse AP. So what about B transpose? P transpose, A transpose, P inverse whole transpose. Now let us call this P inverse or your P transpose itself, or did I do it correctly? P transpose, A transpose, P inverse whole transpose. Yes. So maybe I call the matrix P inverse the whole transpose. Okay. Maybe I call this as my matrix Q, or just P transpose. What I want is, I want Q inverse A transpose Q. So it means I have to take this as my Q. So this is my Q inverse, right? So it's correct. What I wrote was correct. P inverse whole transpose P as Q. So what will be Q inverse then? Q inverse is this, we can interchange. So P transpose whole inverse. So simply P transpose. So instead of P transpose, you have Q inverse, and here this matrix you are considering as Q. So this implies that B or A transpose is similar to B transpose. Okay, fine. Okay. Okay, what happened here? I skipped one page. Okay, the same kind of technique which we did for equivalence matrices, obtaining A, B, P, Q, exactly the same process we have to do for similar matrix as well. Okay, so let us do very simple 2 by 2 case. So you are having standard ordered basis for both domain and codomain, and another basis for domain and codomain. Both are R2 here. Okay, so first let us find A, B, P, and first A and B let us find. So how to find A? Do you all remember? So
V1.
yeah, V1, V2. So TV1 is, what is TV1?
0,
1.
1, yeah.
And what is TV2?
-1,
Minus
0.
1, 0.
Okay. So now what is your A then?
0, 1, -1, 0.
Okay. Now what is, maybe let us Okay, so you have got your A. So what is your B then? Let us say this is U1, U2. So TU1 is
minus
2 1.
1, yeah.
so if you write it in terms of U1 and U2, then what are the coefficients? Maybe I'll write it because it's not straightforward. Alpha times 1 comma 2 plus beta times of 1 comma minus 1. So alpha plus beta is minus 2 and 2 alpha minus beta is 1. So you have 3 alpha equal to minus 1. Right? So alpha is equal to minus 1 by 3. Is that correct?
Yes,
Did I
ma'am.
do any mistakes or is it fine?
It's fine, ma'am.
It's fine, right? Yeah.
Yes, ma'am.
So in that case, what is your beta then? Minus 2 plus 1 by 3. So minus 5 by 3, right?
Yes.
So
Yes, ma'am.
yeah. So you have minus 1 by 3 U1 minus 5 by 3 U2. Okay. And what is TU2?
1 comma 1.
1 comma 1. Yeah. So now again alpha times of 1 comma 2 plus beta times of 1 comma minus 1. So you get alpha plus beta is 1. 2 alpha plus minus beta is 1. So in this case 3 alpha is equal to 2. So you get alpha is 2 by 3. So what is your beta then? 1 by 3. So you get 2 by 3 U1 plus 1 by 3 U2. So what is your matrix B then? Minus 1 by 3.
Minus 5 by 3. 2 by 3.
Minus 5
1
by
by
3. 1 by 3.
Okay, this is your matrix P. Now, if we can find P, then you know how to find P inverse. So what is your matrix P? What is your matrix P? How to find it? You have to express this. P is for the domain and Q is for the codomain, if I am right?
Yes.
That is how we do it, right?
Yes.
So P is given by gamma in terms of beta. So gamma in terms of the ordered basis for beta.
For beta, yes. Maybe you have to take.
Okay, so we have to express gamma in terms of beta. So this is your gamma, you have to express it in terms of beta. So you have to, I guess here it is the standard basis, so we don't have to do anything. So straight away, can you do the matrix?
1, 2, 1 minus 1.
Okay, and what is P inverse? This is a 2 by 2 matrix. So straight away, can you say what is the P inverse?
minus 1.
Yeah. What is the determinant in this case, first of all? What is the determinant of this matrix P you have
minus
written?
3.
Minus 3.
Yeah?
Minus 3.
3.
Minus 3, right? So minus 1 by 3. So inside, what is that you have? You have to do the place change and sign change. Is that correct? Right? This is a shortcut for finding the 2 by 2 inverse, right? So the matrix is 1 by 3, 1 by 3, 2 by 3, minus 1 by 3. The P inverse. Correct? I thought you people are very good in this kind of calculation, but you are not responding. Okay. So it is up to you to verify that B is equal to P inverse AB. We have found all AB, P and P inverse. Okay. So this technique you are all familiar with, right? I think I'm not doing it for the first time.
Yes, ma'am. But ma'am, why did you multiply it with -1/3? I'm confused by that.
It's 1 by determinant of A. Sorry, 1 by determinant of P.
So we have to multiply it, okay? And
Yeah.
minus,
Mm.
okay. And why did you put -1/3?
Because it is determinant is -3.
Okay.
Okay. Okay. So there are few properties of similar matrices. So I just finish with these properties of similar matrices, and other things we will look in the next session. In the next session, please remember that we will be almost completing week 7. So don't miss the class. Very important topics we are going to start. If you don't listen to the next class, then you will be not able to understand the next session, which is on the next Friday. So please don't miss the session on Sunday. Okay. Before coming for the Friday session, at least watch the YouTube video. Then only you will be able to follow the next session. Okay. Fine. So I will just complete this properties of similar matrices. So the very first property is that this is the first property. If two matrices A and B are similar, then they have same rank. Okay. So it means what? You know that if A and B are similar, then you know B is equal to P inverse AP. Okay. B is equal to P inverse AP. So now this means we can rewrite this as PB equal to AP. Is that fine? PB is equal to AB. Is that fine? What I have done in this step? I have simply,
Same.
You brought the inverse there on the left hand side.
yeah. Okay. But I guess this step is not needed straight away. We can tell, I guess. Yeah, either we can use in this way or we can go it in the other way also. So from here, if you see, you can either use this property that if M is invertible, then what is rank of MA? What is rank of PB? From this property, if M is invertible, rank of MA is rank of A. So what is rank of PB? Here P is invertible.
Is a rank of BP.
No, no, no.
Is it?
See, I'm using this property. Rank of MA is equal to rank of A when M is invertible.
Okay.
So here, instead of M, I'm having P, sorry, and instead of A, I'm having B. So what is the right hand side? Rank of
B.
B. Okay. And rank of AP is equal to?
P. Rank of P.
So now I have to use this property. Rank of AM is equal to rank of A if A is invertible. Sorry, if M is invertible.
So A. Rank of A.
Rank of A. Okay. So, and you know that rank of PB is equal to rank of AP. So, you get that rank of A is equal to rank of P. Is that fine?
So, ma'am, we can also argue that since all similar matrices are equivalent matrices and all equivalent matrices have same rank, so similar matrices must have same rank as well.
Yes, you can argue that way also.
Yeah, okay.
Sure. That is the straightforward method, or yeah, that is actually easier method, I can say. This is straightforward, that is easier method. Yeah. So here rank of PB equal to rank of AP. I have used it here to say rank of A is equal to rank of P. Okay. Okay. If two matrices A and B are similar, then they have the same trace. How to use? So here some trace property is given. So how to use this trace property? Trace of AB is same as trace of BA. So how to use this property? Okay, so let us write. You have B is equal to P inverse AP. So now trace of B is equal to, now I consider this as one matrix and this as another matrix. Okay. So I consider P inverse as one matrix, and so trace of P inverse AP. Okay, so trace of P inverse AP. So when I'm considering this matrix as one matrix, so then what happens? So trace of P inverse AP is a trace of AP P inverse, right? So what is then PP inverse? A. Is it fine? How did I do this? Do you all understand?
Yes.
Okay. So you get trace of B is equal to trace of A. What is trace? Again, the sum of the diagonal entries. Okay. So for similar matrix, the sum of the diagonal entries are equal. If two matrices A and B are similar, then they have the same determinant. So determinant property already we know. So determinant of B is equal to determinant of P inverse AP. We know we can split the determinant. Determinant of P inverse, determinant of A, determinant of P. And you know determinant of P inverse is determinant of P whole inverse. And that is why this will become 1 and you will simply have determinant of A. This actually we have done during the determinant property itself. We have proved that determinant of P inverse AP is determinant of A. This we have already done during the determinant topic itself. Okay, so similar matrices will have same rank, same trace, same determinant. Okay, so all these properties are there. So when you are looking for similar matrices, you can see that if any one of them is failed, then you can say they are not similar. But remember, please be careful that even if a matrix have same rank, same trace, same determinant, that does not imply the converse is not true that they need not be similar. Already we saw that these two matrices are not similar, right? We have already verified that these two matrices are not similar. Do you remember the example? A and B are not similar, right? We have already proved earlier that A and B are not similar. I guess we proved somewhere. Yeah, here. A and B are not similar. We have already proved. Okay. So since A and B are not similar, but still you see that all the trace, what is the rank here? You know, rank of A is equal to rank of B is equal to 2. And what is the trace?
2.
2.
2. And what is the determinant?
1.
1.
Yeah. So you see all of them are coinciding, but they are not similar. Okay. So the converse need not be true. Okay. So are these matrices similar? What about their trace?
Not equal.
Not equal. So they cannot be similar, right?
Yes.
So it is very easy to say some matrices are not similar using these properties. What about this one?
The determinants are not same.
Yeah, here the determinant is 6 and here the determinant is
4.
4. So A and B are not similar. Okay. I guess we are almost, yeah, we are done. So some students wanted some examples for isomorphic vector spaces. So I have just added 2 examples here. So please go through this example. I guess this is from your activity question only. And we are using this property only here almost. So try this. If you have doubts in this, maybe we can discuss in the next class. This isomorphism question, I guess I'm not sure exactly whether it is from activity question or from graded assignment. From somewhere I have taken this question. Just go through these questions. If you have doubts, we can discuss. Because specifically some students were asking for questions from isomorphism. That's why I just took these 2 questions. I thought I can discuss if we have time, but already since we are running late, maybe we can discuss it if needed.
Ma'am, can I ask one
Yeah,
simple thing?
yeah.
What is exactly mean by equivalent matrix and similar matrix? Like, what do we exactly get? by determining if it is equivalent or similar?
See, as I told you, the concept of similarity has more importance. For example, let us say you are having a matrix, a very huge matrix, 1,000 by 1,000 matrix or lakh by lakh matrix. Okay, so that is your matrix A, let us say. And suppose you say it is equivalent to a diagonal matrix. Okay, so then the concept of finding determinant, is it simplified?
Yes.
Yes. And there are some concepts which we are not covering in this course, which are called finding eigenvalues. Okay, and these are also very important for data, given set of data. So finding eigenvalues of a system also becomes very easier, because for a diagonal matrix, the eigenvalues are simply the diagonal entries. Okay, but for a given matrix, it has too many computations to find the eigenvalues. First you have to find the determinant, and then you have to solve some polynomial, and then the solutions give you the eigenvalues. So but in the case of a diagonal matrix, you know that straight away the answer is the eigenvalues. Okay, and some cases it is not diagonal matrix, but you get triangular matrices as equivalent matrices. So again, for triangular matrices, the same properties are there, like you know how to easily find the determinant, how to easily find the eigenvalue, such things are there. So that is the significance of studying the similar matrices. Rather than studying the entire system, it is just easier to find study the similar matrix which is in the simplified form. Okay,
Okay.
did I answer your question?
Yes, ma'am. And also, like, what does it exactly mean when two matrices are equivalent?
See, as I told you, two matrices are equivalent means it is actually representing something same. For example, it can be representing the same transformation, but maybe under some different basis. Okay, so it can be representing something, the same concept in different ways, we can say.
Also, like, since in similarity determinant must be same, so can I say that two matrices are scaling by the same amount? Is it also the significance of similar matrices?
Yes, we can say in that way also. Yes.
Oh, okay. And for the equivalent, it need not be
See,
the case that
after
the
all,
two
we are
matrices.
talking about the same transformation, right? Transformation, if a transformation, you know, it is going to scale in the same level. So the corresponding matrices also should be scaling in the same level, right? Yeah.
So, like, determinant of equivalent matrices also is same.
For equivalent matrices, since we are talking about rectangular system, we cannot say that. And also there you don't have inverse, you just have Q. So they are not same for equivalent matrices. Only for similar matrices, you have determinant same.
Okay.
Sorry.
Also, like, what is the last question? So in the similar matrices, you're saying P inverse TP, or let's say P inverse BP, okay? And you're concluding that A and B are similar. And for
Yeah.
equivalent, you are basically taking Q instead of P inverse. So like, Q is not inverse matrix, it is just an invertible matrix, right?
Yes.
That
Yes.
is the difference.
Yes. Yes. Yes.
Okay, okay. Thank you, ma'am.
Okay. Okay. I guess today's concept, everyone understood very clearly. As I told you, in the next session, we will be looking at affine spaces and inner product spaces. And inner product spaces is the beginning of your week 8. So don't miss the next session. Okay. Okay, then. If you don't have any more doubts, we can wind up. Thank you all.
Thank you,
Thank
ma'am.
you.